Each morning when you open a map on your smartphone to check the traffic for your commute, you are accomplishing something that would have been considered pure science fiction merely half a century ago. Without even thinking about it, you are connecting directly with space. This daily convenience represents only the visible part of a massive technological infrastructure that has migrated from orbit to become an integral part of our modern world. Space is not merely a realm of distant galaxies and black holes. It is a technology that serves you in the present moment. To grasp the full extent of our reliance on space, let's begin with the most evident application: the ability to pinpoint our location at any time. The system universally known as GPS, or the Global Positioning System, stands as perhaps the space age's most impactful contribution to everyday life. Yet its origins and the principles that govern its operation are substantially more intricate and compelling than the simple act of catching a signal from a satellite. This system was initially conceived and developed by the American military at the zenith of the Cold War. The objective was straightforward: to equip the Army, Navy, and Air Force with the capacity to determine their coordinates anywhere on the globe with exceptional accuracy, irrespective of the weather or time of day. Before the advent of GPS, navigation depended on ground-based radio signals, inertial systems prone to accumulating errors, or, as a last resort, celestial bodies, all of which were unreliable, imprecise, and lacked global coverage. An orbiting constellation of satellites provided the solution. The inaugural experimental satellite for the system was launched in 1974, and by 1995, it had achieved full operational status for military purposes. The core concept is remarkable in its simplicity. A network of approximately 30 active satellites constantly circles the Earth at an altitude of about 20,200 kilometers. Each one continually transmits a radio signal that carries two vital pieces of information: the precise time of transmission and the satellite's exact orbital position. Your smartphone or vehicle's navigation unit functions as an extremely sensitive radio receiver at this very instant. It captures signals from a minimum of 4 such satellites at once. By knowing the constant speed of light, the device calculates the signal's travel time from each satellite, thereby determining the precise distance to all 4 of them. From there, the process relies on pure geometry through a method called trilateration. If you know your distance from 3 distinct points, your location is where the spheres defined by those distances intersect. The 4th satellite is indispensable for a critical task: synchronizing time. This is where the process transitions from a clever engineering problem to a practical application of the most profound physical discoveries of the 20th century. While every satellite carries an incredibly accurate atomic clock, Albert Einstein's theory of relativity dictates that time aboard these satellites flows at a different rate than it does for us on the planet's surface. This temporal discrepancy is caused by 2 distinct effects. First, according to the special theory of relativity, time slows down for an object the faster it moves. Since GPS satellites orbit at roughly 14,000 kilometers per hour, their clocks lose about 7 microseconds daily compared to clocks on Earth. However, a more potent second effect, described by the general theory of relativity, comes into play. The farther an object is from a massive body like our planet, the weaker the gravitational pull and the faster time progresses. Being high above us in a region of weaker gravity causes the satellite clocks to run ahead by about 45 microseconds each day. When these 2 effects are combined, the clocks on GPS satellites effectively gain 38 microseconds every single day relative to terrestrial clocks. This might appear to be an insignificant variance, but for a system that relies on precise timing, it is a catastrophic flaw. If engineers hadn't accounted for these relativistic corrections, the coordinate error would accumulate at a rate of about 10 kilometers per day. Your navigator would place you on an adjacent street within minutes, and in a completely different city after a day. So the next time you use your phone to find the nearest coffee shop, it's worth remembering that you are relying on Einstein's theory of relativity to do so. Initially, access to high-precision GPS data was restricted to the military, with the civilian signal being intentionally degraded to an accuracy of about 100 meters. This all changed on May 2, 2000, when this limitation was officially removed, altering the world forever. Today, GPS serves as the operational backbone of modern civilization. Logistics firms monitor every container and vehicle, optimizing delivery routes to save billions on fuel. Farmers employ precision agriculture systems, allowing satellite-guided tractors to distribute fertilizer with centimeter-level accuracy, which boosts crop yields while minimizing environmental impact. Emergency responders can locate lost individuals in remote areas using the signals from their phones. Even global financial markets are dependent on GPS, as the highly accurate timestamps from its satellites are used to synchronize high-frequency trading operations across the world. Geologists utilize the system to monitor the movement of tectonic plates with millimeter precision, aiding in the prediction of earthquakes. We have constructed a society that is fundamentally unable to operate without this invisible network orbiting far above our heads. And this is merely one technology that has come to us from space. If GPS acts as an unseen assistant, another space-based technology provides results we observe daily on our screens. Weather forecasting. The ability to know if you should carry an umbrella or how to plan a weekend trip feels entirely commonplace. Yet this convenience is supported by the immense efforts of a global network of meteorological satellites. Without them, any weather prediction would be little more than a guess, and we would only become aware of approaching hurricanes or typhoons when the wind was already tearing roofs from buildings. The vantage point of space has granted us the profound gift of viewing our planet in its entirety, allowing you to witness the formation and travel of the massive atmospheric systems that dictate our weather. This capability has not only transformed your daily routines, but has also been instrumental in preserving an immeasurable number of human lives. You'll find there are two primary categories of weather monitoring spacecraft. The first type, geostationary satellites, maintain a position nearly 36,000 kilometers above the equator, their orbits perfectly synchronized with Earth's rotation. To you on the ground, this makes them appear stationary, enabling them to provide uninterrupted surveillance over a single enormous region, like an entire continent and the adjacent oceans. These are the satellites responsible for the captivating time-lapse videos of cloud patterns you see on weather reports. They are our frontline defense, spotting the genesis of tropical cyclones over the ocean and monitoring their path and intensity. This gives emergency services crucial days, rather than mere hours, for preparation and evacuation. A stark contrast to the pre-space era, when such storms were unforeseen and lethal killers. Because of this orbital perspective, fatalities from these events have dramatically fallen by a factor of 10. The other major category consists of polar orbiting satellites, which operate at significantly lower altitudes, typically between 800 and 1,000 kilometers. By traversing a path over the planet's poles, they can survey nearly the whole of Earth's surface within a 24-hour period as the globe spins beneath them, much like a scanner meticulously moving across a document. From their lower orbit, these spacecraft capture far more detailed imagery and gather an extensive array of additional data. Their instruments measure everything from the temperature of the ocean surface and the height of waves to ozone levels, air pollution, and even the moisture content of the soil. Information from dozens of such satellites, operated by various nations, is continuously streamed to global weather centers. At these centers, powerful supercomputers digest trillions of these data points to construct sophisticated mathematical models of our atmosphere. It is from these complex simulations that you get the familiar 5 or 10-day weather forecasts you depend on. The remarkable precision of today's predictions is a direct consequence of the constant operation and enhancement of these observers in space. Yet space has offered us far more than a new way to watch our own planet. It has also given us the means to communicate across immense distances. In fact, satellite communication is another foundational pillar supporting our interconnected modern world. While initial experiments took place in the 1960s, the true revolution began with the deployment of satellites into geostationary orbit. A strategic arrangement of just 3 of these satellites positioned equidistantly above the equator can blanket nearly all of Earth's populated areas with a communications signal. This is the technology that enabled live broadcasts of events like the Olympic Games across continents and provides vital links for ships at sea, planes on international routes, and isolated research outposts in Antarctica. More recently, you've seen the start of a new communications revolution with the rise of global, low-orbit constellations such as Starlink. The concept involves launching thousands of smaller, more affordable satellites into orbits only a few hundred kilometers high, replacing the traditional model of a few massive ones. These devices speed across the sky, seamlessly relaying signals between each other to maintain a continuous connection. This network design accomplishes 2 key goals. It drastically cuts down on signal latency, which is essential for activities like video conferencing and online gaming, and it delivers high-speed internet to virtually any location on Earth. This is more than a simple convenience. For millions in developing nations or isolated areas, it represents a chance to connect to global education, healthcare, and economic opportunities. It is a technology that dismantles geographic boundaries and has a profound, life-altering impact. Furthermore, a large number of satellites, including those used for navigation and weather, carry payloads for the International Search and Rescue System, SOSPAS-SARSAT. In an emergency, any vessel, aircraft, or personal locator beacon can transmit a distress call that is picked up by a satellite and instantly forwarded to rescue coordinators. This network, born from a collaboration between nations like the USSR and the USA during the peak of the Cold War, is responsible for saving thousands of people annually, demonstrating that space can be a powerful arena for cooperation. So far, I've covered unseen navigation grids and worldwide communication systems. But the impact of space exploration is far more concrete than you might imagine. You can find its influence in your hands, your kitchen, medical facilities, and even the clothes you wear. The race to space was more than an ideological contest. It was a tremendous accelerator for advancements in materials science and medicine. Engineers had to solve problems never encountered before, such as designing materials that could endure temperature swings from negative 100 degrees Fahrenheit 50 to positive 150 degrees Celsius. They also had to shield astronauts from the vacuum and radiation of space while inventing alloys that were both lightweight and extraordinarily durable for building rockets. Numerous solutions developed for these specific challenges ultimately made their way into surprisingly common aspects of our daily existence. The best-known instance of this is likely the non-stick coating Teflon. While the material was found by chance prior to the space age, NASA pioneered its extensive use in the 1960s for insulating equipment and as a component of heat shields. Contrary to a common myth, NASA did not invent the Teflon pan, but the material's immense popularity and integration into household products owe a great deal to its high-profile use in the space program. A more direct and significant technological inheritance comes in the form of shape memory materials. Typically composed of nickel and titanium, these remarkable alloys possess the ability to remember their initial form. When a component crafted from this material is bent or distorted, applying heat will cause it to revert perfectly to its original configuration. In the realm of spaceflight, certain alloys are employed to fashion self-deploying structures like antennas and solar arrays, which need to be compact for launch. This same technology has had a revolutionary impact on medicine here on Earth, where these materials are commonly found in orthodontic braces that apply steady, gentle pressure to align teeth. Perhaps their most critical medical application is in vascular stents, which are tiny mesh tubes. A stent is inserted into a diseased, constricted artery in a compressed form, and once inside, the body's warmth causes it to expand back to its preset shape, thereby propping open the artery walls to re-establish proper blood flow and prevent a heart attack or stroke. To shield astronauts and their spacecraft from the extreme cold of outer space, engineers created exceptionally lightweight, multi-layered blankets from metallized film. These reflective space blankets are now a standard item in emergency medical kits and survival gear on Earth, weighing next to nothing while effectively preserving body heat to save individuals from hypothermia following accidents or natural calamities. The advanced technologies created for the heat-resistant coatings on space shuttles have also become the foundation for contemporary fire-retardant materials in firefighters' protective gear. Even the shock-absorbing soles in today's athletic shoes are a direct descendant of materials engineered for astronaut boots, which were designed to soften the impact of walking on the moon's surface. Similarly, the development of cordless tools like drills and vacuum cleaners was significantly accelerated by the needs of space exploration. Astronauts working in zero gravity required potent, self-contained instruments free from cumbersome cables, prompting NASA to invest substantially in efficient electric motors and high-capacity batteries, which paved the way for the wide array of cordless consumer electronics we use today. Medicine represents another field that space exploration has fundamentally reshaped. The challenge of continuously tracking astronaut health from immense distances spurred the innovation of telemetry and remote diagnostic systems. In fact, the sensors worn by Yuri Gagarin can be seen as the forerunners to the modern portable heart monitors now widely used by athletes and individuals with cardiac issues. Advanced water purification techniques, originally engineered for the International Space Station, where water recycling is critical, are now being implemented in filtration systems that provide clean drinking water to remote regions on Earth. Even the common digital ear thermometer is a direct application of the infrared sensing technology astronomers first used to determine the temperatures of far-off stars and planets. Furthermore, the development of magnetic resonance imaging devices, or MRI, was made possible by digital signal processing methods perfected in NASA labs to sharpen images from the moon and other celestial bodies. The catalog of such spin-offs is nearly endless, including everything from freeze-dried foods to robotic computer vision. These innovations, which have improved our safety, comfort, and health, are all direct or indirect byproducts of our drive to explore beyond our terrestrial home, revealing space as a rich wellspring of transformative ideas. In the profound darkness of space, an event unfolded that baffled the global astronomical community. During the autumn of 2017, telescopes registered an extraordinary object, an interstellar traveler that challenged all existing classifications of celestial bodies. This enigmatic visitor was given the name Oumuamua, a Hawaiian term for a scout from a distant past. a designation that would prove remarkably fitting. Resembling a gigantic cosmic needle, elongated to 10 times its width, this object sliced through the edges of our solar system, seemingly carrying secrets from another star. Its surface possessed a metallic sheen, reflecting sunlight with 10 times the intensity of a typical comet or asteroid, which gave it the look of a burnished, reflective artifact. The truly perplexing behavior began as Oumuamua swung around our sun. The object inexplicably picked up speed, moving as though propelled by an unseen engine. This acceleration contradicted the known laws of orbital mechanics and prompted intense speculation among scientists about whether it could be an artifact from an alien civilization. Scientists now theorize that this interstellar visitor was ejected from its native system by a cataclysm, such as a planetary impact or a star's explosion, and sent on a journey through the void. After drifting through interstellar space for what could have been millions of years, it was temporarily snared by our sun's gravity. Astronomers eventually discovered that Oumuamua was composed not of water ice, but of solid hydrogen, a material that can only form in the extreme cold between stars. As this hydrogen shell, which had accumulated over 500 million years of travel, was heated by the sun, it began to vaporize, producing the puzzling propulsive effect that explained its strange acceleration. The object's distinctive reddish color suggested it had been exposed to cosmic radiation for a vast amount of time, staining its surface over eons. In response to its discovery, Project Lyra was proposed as an audacious mission to intercept the departing traveler, employing gravity assists from Earth and Jupiter to act as a powerful cosmic slingshot. A different proposal envisioned launching 1,000 minuscule probes, each weighing no more than a matchstick but fitted with a solar sail the size of a boxing ring, which would be pushed by Earth-based lasers to 20% of the speed of light. Not long after Oumuamua's passage, a second interstellar guest, Comet Borisov, was identified, having been discovered by the amateur astronomer for whom it was named. In contrast to its predecessor, Borisov displayed much more conventional cometary characteristics, expelling more than 400 pounds of cosmic dust each second and revealing a high concentration of carbon monoxide. The nature of its polarized light and the smoothness of its gas cloud offered scientists a narrative of an object that had traveled through intergalactic space without ever interacting with other stars. The appearance of these cosmic travelers spurred the classification of an entirely new type of celestial body, dark comets. While they behave just like comets, their appearance is almost identical to that of asteroids. Within our solar system, 14 such bodies have been identified and sorted into two distinct groups: the outer dark comets, which are hundreds of feet across and follow elongated orbits, and the inner dark comets, measuring tens of feet in diameter and favoring circular paths near the inner planets. These enigmatic objects could account for anywhere from 0.5% to a full 60% of all near-Earth bodies, a realization that profoundly reshapes our conception of the cosmic population in our planetary neighborhood. Spectral analysis of their radiation has shown that ice is hidden beneath their rocky exteriors, which produces the same kind of jet propulsion seen in ordinary comets when heated. When subjected to centrifugal forces, these bodies can shatter, creating an entire swarm of smaller fragments, each one prone to further disintegration. These interstellar guests are connected to the theory of panspermia, which posits that life could be transported between different star systems. This idea suggests that microscopic organisms might be able to survive journeys lasting millions of years through the vacuum of space while in a frozen state. Astronomers have determined that if an object the size of Oumuamua were to strike the Earth, it would unleash a blast wave powerful enough to obliterate an entire nation, while a collision with the ocean could spawn tsunamis as high as skyscrapers. To counter such dangers, Various planetary defense strategies are currently in development, ranging from kinetic impactors to precisely controlled explosions designed to shift the course of a potentially threatening object. The most imaginative concepts even entertain the idea of fitting asteroids with rocket engines, effectively transforming them into controllable vessels for our own interplanetary voyages. The discovery of dark comets has initiated a new era in our comprehension of ice distribution throughout the solar system, demonstrating that water reserves can persist even in areas once thought to be excessively warm for frozen water to survive. Computer models simulating the trajectories of these objects over a 100,000-year period indicate that a large number of them likely originate from the inner parts of the asteroid belt, which is situated between Mars and Jupiter. Due to the dynamic instability of near-Earth space, this population is replenished approximately every 10 million years, ensuring a steady stream of new celestial visitors. The investigation of interstellar objects presents humanity with a unique chance to utilize them as naturally occurring cosmic taxis for venturing to faraway stars. To embark on such a journey, one would only need to achieve orbit around one of these wanderers to secure a complimentary ride into the void between stars. Every new arrival from the depths of space carries with it a fragment of the history of other worlds, offering us a glimpse into the formation of planetary systems across the galaxy. It is conceivable that among these cosmic drifters are the very keys to unlocking the origins of life on Earth and understanding its proliferation across the cosmos. Contemporary astronomy is confronted with a curious paradox. The further we gaze into the cosmic expanse, the more blurred the finer details of distant worlds become. Stars resolve into mere points of light. Exoplanets are only faintly visible through our most powerful telescopes, and vast disks of cosmic debris appear as indistinct smudges. Yet the universe seems to accommodate our curiosity by sending us messengers from other star systems, veritable living textbooks that can unlock the secrets of how distant worlds are born and evolve. I want you to picture a vast, spherical shell that envelops our entire solar system, much like an enormous soap bubble. This is the Oort cloud, the most remote frontier of our cosmic residence, where billions or perhaps even trillions of mountain-sized icy fragments drift in perpetual cold. In stark contrast to the planets, which have orbits neatly aligned on a flat plane around the Sun, this ethereal cloud encloses us on all sides, forming a thick-walled sphere of frozen pandemonium. Scientists even theorize that interstellar travelers might actually be more numerous than the native inhabitants in this far-flung region. Although no human has ever directly witnessed the Oort cloud, astronomers have inferred its presence by analyzing the trajectories of comets. This enigmatic shell might have been formed from the residual material of the early solar system, but an alternative view from some researchers proposes that a large fraction of it could be composed of interstellar interlopers captured over eons. Not long ago, a comet designated 96P/Mach-Holtz-1 was observed plunging toward the Sun, and this 6-kilometer icy nomad is a strong candidate for an object that originated outside our solar system. A joint effort between the European Space Agency's Solar and Heliospheric Observatory and NASA is carefully tracking its trajectory. As solar radiation heats its frozen core, a trail of gas streams out behind it. Comets can sometimes exhibit two distinct tails, one made of dust and the other of gas, which can extend for hundreds or, in some cases, millions of miles. An analysis of materials from 150 comets conducted in 2008 revealed that Mach-Holtz has an unusually low carbon content and is deficient in other common components. This peculiar chemical signature could point to an origin beyond our solar system. It's plausible that the gravitational pull of a massive planet once flung this object from its home system, sending it on a long journey through interstellar space until it was eventually captured by Jupiter. The gas giant could have then altered its path, locking it into an orbit around our Sun. An alternative hypothesis suggests the comet originated in a poorly understood area within our own solar system, and its strange makeup is the result of its numerous passes around our star. For now, scientists are awaiting the comet's close approach with an excitement that rivals the anticipation of a holiday. With that, we conclude our exploration of these mysterious visitors from the great beyond. The vast majority of comets that plunge into the Sun measure no more than 32 feet across and are incinerated as they approach our star. Yet the immense size of Comet Machholz, which is over 2/3 the height of Mount Everest, seems to be what saves it from being completely vaporized. This leads us to the human mind's incredible capacity for drawing lines between phenomena that appear to have no connection at all, such as strange clouds over Stonehenge, the migratory patterns of Canadian wolves, designs on the wings of Caribbean butterflies, or mysterious markings on the lunar surface. While these may seem like isolated facts, people can weave them together into a single, cohesive narrative. Picture this. You read the far-fetched story on some obscure website, dismiss it, and then begin to perceive minor details in your surroundings that appear to validate what you read. You come to feel that you've discovered something extraordinary, yet for some reason, others either fail to see it or outright deny it. Your attempts to share this newfound knowledge are met with total bewilderment, and some might even label you as delusional. In 2017, a disreputable website circulated a tale about a spacecraft named the Black Knight, which had supposedly been monitoring humanity for 12,000 years before agents from a clandestine organization finally destroyed it. The entire premise sounds like utter fabrication or the storyline of a low-budget science fiction movie. However, years later, you happen upon a story concerning Nikola Tesla. In 1899, the renowned scientist was in his Colorado Springs laboratory, carrying out radio experiments. All of a sudden, his equipment detected an unusual signal, which was followed by another after a short interval. These signals repeated at precise intervals, suggesting an attempt to convey a message. Tesla speculated that it could be a communication from an extraterrestrial civilization, employing the universal language of mathematics, an event he documented in a journal at the dawn of the 20th century, noting his inability to decode it. Then, in 1927, an engineer from Oslo with a passion for radio technology transmitted signals into deep space. He was astounded when, after a period of time, those very same signals returned to his receiver, as if bouncing off a massive object, or as if an entity was capturing his messages and sending them back to initiate contact. This man promptly reported his findings to scientific journals, and it's conceivable that someone linked this occurrence to Tesla's accounts of peculiar signals from the cosmos. During the 1960s, Time magazine ran an article which asserted that the United States had identified a satellite orbiting our planet that utilized technology unknown to us. A few years after that, Gordon Cooper, an astronaut from Project Mercury, claimed to have witnessed a peculiar object while on a space flight. But the Black Knight only achieved widespread notoriety in the late 1990s, when the National Aeronautics and Space Administration, or NASA, published a collection of images showing a mysterious object captured during the inaugural flight to the International Space Station, where astronauts had spotted and photographed its odd shape. Someone eventually compiled all these separate facts, proposing that this enigmatic satellite had been circling our world for over 10,000 years. Its age was calculated from the radio transmissions that Tesla and the Norwegian engineer had received. If this were true, the Black Knight would have arrived during the age of ancient Egypt, predating the Egyptians themselves. It might have aided in the construction of the pyramids and great temples, all while observing our progress and relaying that information to a distant world. This led people to suspect that NASA and other space agencies were concealing information about the object to avert global panic. Once you assemble all the data concerning this cryptic satellite, you might start to believe that the bizarre article you once read could hold some truth. The claim is so fantastic and outlandish that it seems no one would ever take it seriously, aligning with the principle that the best way to conceal something is to place it in plain view. Driven by this idea, you and other enthusiasts begin hunting for information about the mysterious ship, creating online forums, sharing photos of unidentified objects, and developing a fixation on the subject. At this point, congratulations. You've become the perfect conduit for spreading tabloid hoaxes.
The appeal of these myths and urban legends lies in the human brain's affinity for uncovering supposedly hidden knowledge. The rush of adrenaline and the shock of a concealed truth can foster a kind of psychological dependency. Adherents of the Black Knight story believe Tesla intercepted signals from an alien race, but they conveniently ignore scientific papers that explain how such radio signals can be produced by colossal cosmic bodies like pulsars, which are rotating neutron stars that emit intense beams of electromagnetic radiation. Space is filled with these kinds of signals, none of which require an intelligent source. The tale of the Norwegian engineer has yet to be fully explained, but the phenomenon of signals returning as an echo has no connection to a flying object. Furthermore, the very same Time magazine article about the strange satellite also mentioned that it was merely a piece of an American reconnaissance satellite, a detail that myth supporters tend to overlook. As for astronaut Gordon Cooper, he never actually saw anything of the sort, and even produced a mission transcript that contained no reference to a black satellite whatsoever. The primary evidence cited for the Black Knight's existence remains the photographs from that first mission to the International Space Station. While the astronauts did indeed spot and photograph an unusual object, it was no mystery to them. During external maintenance, a segment of the spacecraft's thermal covering had detached. What was photographed was simply a fragment of thermal insulation. A few days later, this supposed Black Knight deorbited and was consumed by Earth's atmosphere, with a NASA engineer later confirming that the famous images showed nothing more than a common piece of the spacecraft. Despite the fact that every piece of this myth has been thoroughly debunked for a long time, the Black Knight continues to persist in the public consciousness and on the pages of the tabloid press. It is transformed into a thread connecting numerous reports of strange flying objects, evolving from a supposed physical entity into a powerful cultural phenomenon. The classic symbol of extraterrestrial visitors, the flying saucer, has fallen out of fashion. Today, that symbol is a strangely shaped black stone. It's a common understanding that you can't hear any sound in the vacuum of space, whether it's talking, laughing, or screaming. Yet in specific environments like the superheated gas enveloping the black hole in the Perseus cluster, space can actually be remarkably loud. This galactic cluster is situated 250 million light-years from Earth, and scientists have managed to record the authentic sound of space, pressure waves propagating through its plasma. Although the realization that black holes could produce acoustic signals dates back to 2003, this was the very first instance where those signals were converted into a form that the human ear could perceive. Nearly a decade ago, a NASA probe made a startling discovery on Titan, one of Saturn's moons, revealing the presence of profound canyons. These vast gorges, which are roughly half a mile across, bear a striking resemblance to the Grand Canyon, but are uniquely submerged in liquid hydrocarbons. This landmark observation marked the first time that liquid-filled canyons and channels had ever been identified on the surface of Titan. You're likely aware that our solar system is populated with countless small particles and large rocks that circle the Sun, much like planets. While most of these meteoroids and comets originate within our system, from places like the asteroid belt or the Kuiper belt, scientists encountered a true anomaly 5 years ago. They identified a peculiar, reddish, cigar-shaped object named Oumuamua, which measured over 3,000 feet long and was the first known interstellar visitor to traverse our solar system. What made Oumuamua so remarkable was not just its size, but its incredible speed, far exceeding that of our native asteroids and comets. The exact origin of this enigmatic object remains a complete mystery, as its journey likely began millions or even billions of years ago. Since the stars have shifted their positions over such a vast timescale, tracing its path back to its home system is an incredibly challenging task. You might think of the Sun as a simple burning sphere, but it's actually an intricate system of massive plasma fountains, complex magnetic fields, and strange matter formations that can be 500 times larger than Earth. This solar activity ebbs and flows in a natural rhythm that repeats approximately every 11 years. As this cycle approaches its conclusion, the Sun's magnetic fields along its equator weaken and collide, leading to a decrease in solar eruptions and sunspots. This period of weakening magnetic activity triggers the creation of colossal plasma tsunamis, which are the most potent storms in our solar system, surging across the Sun's surface for weeks. These powerful events can bend, fracture, and launch solar material into space, posing a significant threat to our power grids on Earth. The cycle then restarts as large sunspots reappear near the Sun's powerful magnetic field lines. Though scientists are still uncertain why these tsunamis form, or why they appear specifically at the end of the cycle. Evidence suggests that what appear to be ancient shorelines on Mars were actually carved by a pair of massive tsunamis billions of years ago. These cataclysmic events were triggered by the longest landslide ever recorded in our solar system, where a cascade of rocks from a mountain crashed into a body of water. The resulting colossal waves surged across the Martian terrain for hundreds of miles, scraping the ground and depositing sandy ridges near Olympus Mons, which strongly supports the idea that Mars once harbored an ocean. Following the visit of Oumuamua, our solar system hosted another interstellar guest, a comet named Borisov, which boasted a tail extending over 100,000 meters. First photographed in 2019, it was distinguished by a brilliant white aura, a key indicator that it originated outside our solar system, likely from a frigid region akin to our own Kuiper belt. A prevailing theory posits that it may have formed around a red dwarf, the most abundant type of star in our galaxy. But its high velocity gave scientists only a few weeks to observe it before it sped past our world. Finding new planets is always a source of great fascination, and 2017 was no exception when astronomers announced the discovery of a super-Earth just 21 light-years away. This exoplanet, which orbits a star beyond our own, possesses a mass nearly 3 times that of our world. It circles its M-class dwarf star so quickly that it completes a full year in only 2 weeks, placing it closer to its star than Mercury is to our Sun. Despite its proximity to its star, the planet could potentially harbor liquid water, as dwarf stars are significantly cooler than our own Sun. The term super-Earth describes planets that are more massive than Earth but lighter than ice giants like Uranus and Neptune, and they can be composed of rock, gas, or both. This particular world is especially captivating to scientists because it raises the tantalizing possibility of supporting life. In 2005, during his final spacewalk as commander of the International Space Station, Leroy Chiao witnessed a strange phenomenon.
5 lights moving alongside him in a pyramid-like arrangement. When he queried his fellow spacewalker, his colleague reported seeing nothing at all. Later analysis of satellite imagery led investigators to a plausible explanation. Chow had likely observed the powerful lights of fishing boats off South America, whose illumination, combined with Earth's rotation, created the illusion of airborne objects.
When a colossal star exhausts its fuel and explodes in a supernova, its core implodes under its own gravity to create a neutron star, the densest material known to exist. For a few brief seconds during this transformation, the energy released is equivalent to the combined light of every star in the visible universe. To grasp the mind-bending density of a neutron star, picture the entire island of Manhattan crushed down into a sphere containing 1.5 times the mass of our Sun. Were it any denser, it would inevitably collapse and form a black hole. Not long ago, astronomers witnessed the cataclysmic collision of 2 neutron stars. This event of immense power generated gravitational waves that distorted the fabric of space itself, all while forging heavy elements such as platinum and gold. If you could journey away from our planet and look back, you would see it glowing like a festive ornament. By night, our sprawling cities appear as vibrant yellow clusters, while in the daylight, you can discern peculiar human-made structures like the palm-shaped island in the United Arab Emirates, or the dark, winding line of the Great Wall of China. Yet, when you aim a telescope at our neighboring planets, a starkly different view emerges. Mars reveals itself as a vast, unending desert, and Venus is a landscape of nothing more than rock and volcanoes. Even as our view extends into the far reaches of the cosmos, we encounter only desolate, apparently lifeless worlds, devoid of any hint of extraterrestrial civilizations. Despite this, the conviction that life on Earth is not a singular event is widely held, considering our galaxy contains billions of sun-like stars, and the observable universe holds billions of similar galaxies. With a virtually limitless number of stars, the potential for habitable worlds around them seems immense. It's conceivable that we have not yet detected life on other planets, simply because it remains concealed beneath their surfaces. Take Europa, one of Jupiter's moons, which is just slightly smaller than our own moon. Its internal structure is often compared to a soft-boiled egg, with a solid, icy shell acting as its crust. If you were able to drill through this thick ice, you would eventually break through to a vast, liquid ocean of water. Given that Jupiter and its moons are so distant from the Sun, the temperature there plummets to about 270 degrees below zero, a cold that should freeze any water instantly. However, the immense gravitational pull from Jupiter generates powerful friction deep inside Europa, which warms its core. This internal heat is sufficient to melt the overlying ice from below, sustaining a hidden, subsurface ocean. Since water is the cornerstone of all known life, it's plausible that this ocean could host simple bacteria. But beyond that, one can imagine even more complex organisms. Perhaps strangely shaped fish adapted to low gravity, or even whale-like beings that filter feed on alien plankton. In 2009, astronomers found the planet GJ1214b, a world believed to be completely enveloped in a global ocean. Located about 40 light-years away, this exoplanet has a mass composed of roughly 75% water. The issue is that its surface temperature is incredibly high, causing the water to vaporize into a strange, superfluid state. This vapor is so compressed that it achieves a density nearly equal to that of liquid water, creating conditions under which life as we know it could not survive. More recently, scientists have pinpointed at least 24 exoplanets that might be even more suitable for life than our own world,
terming them superhabitable. These planets orbit their stars within the habitable zone, an area at the perfect distance where conditions are just right for liquid water. In our own solar system, this zone encompasses Venus, Earth, and Mars. An ideal superhabitable world would likely be about 10% larger than Earth, with stronger gravity to maintain a thicker atmosphere and a temperature roughly 8 degrees higher, which would promote a more humid climate and a richer diversity of life.
The most definitive sign of an advanced, intelligent civilization would almost certainly be their radio waves. Picture a habitable world, much like Earth, where evolution has given rise to intelligent beings. Perhaps they are taller than humans due to lower gravity, or their eyes are adapted to a brighter star. Inevitably, such a civilization would likely develop radio technology for communication, broadcasting signals that you could think of as a powerful sound blasting out into the cosmos. Right now, Earth itself is a source of significant radio wave emissions. The amount of noise radiating from our planet is quite substantial. If a civilization on a nearby planet had radio telescopes capable of capturing these waves, they would know that our world is teeming with life. Here on Earth, we have arrays of radio telescopes aimed at deep space, listening patiently for just such a signal from another world. So far, the cosmos has been silent, but this doesn't mean there aren't planets out there broadcasting. The greatest barrier to communication is sheer distance. Imagine we travel 200 light-years to another star system, where an inhabited world, let's call it Planet X, exists. If that civilization developed radio technology and sent its first message into space, our telescopes would not be able to detect it for 200 years. The same delay applies in reverse. Humanity has only been using radio communication since 1895, meaning our earliest signals will not reach that planet until the year 2095. Only then could they possibly hear our voice. Furthermore, this period of intense radio noise from a planet might be quite brief. As our own technology advances each year, our level of radio interference actually diminishes. The increasing use of mobile networks, cable television, and fiber optics channels our communications more efficiently, making Earth progressively quieter and less visible in the radio spectrum. It stands to reason that the same could be true for any advanced civilization, meaning their radio signature might be just a fleeting flash on a cosmic timescale. Therefore, we cannot interpret radio silence as definitive proof that we are alone. Everything could change if we developed a telescope powerful enough to capture a direct photograph of a potentially habitable exoplanet. By magnifying such an image, you might see the glimmer of alien cities with towering structures and massive antennas. For the time being, however, our vision is limited. Even the pictures we take of Mars and its moons can be deceptive. For instance, a region on Mars called Cydonia contains a landform that looks remarkably like a human face, leading to speculation about ancient civilizations building vast monuments. Some of the more imaginative theories even suggested it was the fossilized remains of a giant humanoid. The reality, of course, was that it was simply a hill sculpted by powerful winds, with shadows falling in its craters to create the illusion of eyes and a mouth. You might also consider the monolith on Phobos, a moon of Mars, where a smooth stone stands nearly as tall as the Great Pyramid of Giza. This discovery fueled countless theories of alien construction, but it was ultimately identified as nothing more than a natural rock formation. Even so, the infinite number of stars and the worlds that orbit them makes the existence of other civilizations an almost statistical certainty. So, what prevents extraterrestrial civilizations from visiting Earth? A common assumption is that life everywhere follows a comparable path, from simple organisms to evolution and eventually a high-tech society. However,
A civilization on the brink of space exploration could be annihilated by a colossal meteorite impact, similar to the event that erased the dinosaurs, resetting the evolutionary clock on their world.
Furthermore, the more technologically sophisticated a society gets, the higher its chances of self-annihilation. For instance, researchers working with something like the Large Hadron Collider might unintentionally generate a miniature black hole. Such an anomaly would start devouring its surroundings, expanding until the civilization's advanced cities and its entire home world vanish without a trace. There's also the idea that highly developed species could navigate wormholes, which are theoretical shortcuts through space-time connecting different universes. It's conceivable they might journey through these passages and find no reason to come back. Alternatively, the very existence of life on our planet might be an extraordinary anomaly, the result of an improbable sequence of fortunate events. Consider, for example, our solar system's position within the Milky Way galaxy. Our galaxy is frequently lit up by supernova events, which unleash deadly radiation that sterilizes everything for immense distances. We just happen to be in a galactic orbital path that keeps us safely shielded from the devastating effects of these cosmic blasts. The Moon represents another critical piece of the puzzle. A leading hypothesis proposes that roughly 4.5 billion years ago, a Mars-sized object collided with our young planet. A direct hit would have obliterated Earth, while a glancing blow would have sent the fragments scattering into space. Instead, the impact occurred at just the right angle, trapping a portion of the object in our orbit to coalesce into the Moon. This newly formed moon was instrumental in stabilizing Earth's spin on its axis and, through its gravitational pull, heating our planetary core. This internal heating was the catalyst for the development of our magnetic field, the essential shield that protects all life from the constant barrage of the solar wind. This sequence of events suggests that conditions for life might be incredibly rare. It's also worth considering that life elsewhere might not share our biochemistry. While our bodies are fundamentally built on carbon and water, alien life could use silicon or phosphorus as a substitute for carbon, and ammonia or methane instead of water. Atoms like these could create molecules with diverse structures, potentially giving rise to organisms completely foreign to anything we've ever observed on our own world. Life on our beautiful world might feel secure, but that feeling lasts only until you contemplate the dangers that lurk in the infinite darkness of space. Let's examine some scenarios that could spell the end for planet Earth, starting with a hypercane, a natural disaster of extreme intensity. A hypercane is a hypothetical storm of unimaginable force, which could be set in motion if the oceans become excessively warm from climate change or a major volcanic event. Such a storm would tower high into the stratosphere, far beyond a typical hurricane, with wind speeds hitting 500 miles per hour and incredibly low internal pressure. It wouldn't break apart easily and could rage for weeks, potentially tearing a hole in the ozone layer as large as North America. Extremely destructive tornadoes present another significant danger. A tornado is essentially a fiercely spinning column of air that connects a thunderstorm to the ground. They form within thunderclouds where rising warm wet air and sinking cold air with rain or hail establish rotating currents. These spinning air currents, which start out horizontally, can then tilt vertically and drop from the cloud base to become a full-fledged tornado. Tornadoes can manifest as thin, rope-like vortices or as massive, tangled funnels, and they are categorized using the enhanced Fujita scale. A weak tornado might last only a few minutes, with winds not exceeding 100 miles per hour. A strong one can persist for about 20 minutes with wind speeds nearing 200 miles per hour,
while violent tornadoes last over an hour with winds between 200 and 300 miles per hour.
The United States sees an average of about 1,000 tornadoes each year, with many concentrated in a region known as Tornado Alley, which covers 10 Midwestern states. One of the most destructive on record tore through 3 states, setting a world record by traveling 220 miles. Now, imagine a tornado far more powerful, capable of sweeping across entire continents and leaving nothing but devastation in its wake. Supercell thunderstorms, while being the least common type, are by far the most hazardous. These storms are notorious for generating severe weather, including damaging winds, exceptionally large hail, and powerful tornadoes. What sets a supercell apart is its core feature, a deep, sustained, rotating updraft known as a mesocyclone, which allows the storm to last for hours and inflict immense damage. Of course, an asteroid impact remains a potent threat, capable of extinguishing all life. A sufficiently large celestial object would trigger widespread devastation, mirroring the 9-mile-wide asteroid that struck our planet 66 million years ago. That event is credited with eliminating 75% of all plant and animal species, most famously the dinosaurs. The severity of such an impact would depend on the asteroid's size and velocity, potentially causing enormous firestorms, colossal tsunamis, and a nuclear winter scenario. This occurs when ejected debris fills the atmosphere, blocking sunlight and causing a catastrophic shift in the global climate. The good news is that our current technology would likely spot a large incoming asteroid long before it reaches us, giving us precious time to try and counteract the danger. Our very own Sun, a colossal and perpetually shifting sphere of incandescent gas, holds the potential to orchestrate the end of our world. It periodically unleashes immense bursts of energy, known as solar flares, which are frequently associated with coronal mass ejections, vast bubbles of ionized gas that can be propelled to astonishing velocities. A single solar flare can release 10 million times more energy than the most powerful volcanic eruptions, expelling billions of tons of charged particles in a matter of minutes at temperatures that soar to several million degrees Fahrenheit. Astronomers theorize that these powerful eruptions of solar radiation happen when the sun's magnetic field in specific areas becomes intensely tangled and twisted. Eventually, this accumulated energy is violently discharged, causing the star to radiate light and particles consisting primarily of electrons and protons. While most solar flares are brief, lasting only a few minutes, some can persist for several hours, creating a sustained threat. Scientists categorize solar flares according to the brightness of their X-ray emissions. The smallest of these would be virtually undetectable without specialized instruments. Medium-sized flares might cause temporary radio blackouts near the poles, but pose no significant danger. The real concern lies with X-class flares, which are responsible for generating the most powerful and longest-lasting solar storms our planet can experience. Imagine if your vision could perceive gamma rays. You would witness extraordinarily brilliant flashes appearing daily, briefly overpowering everything else in the sky before vanishing. These phenomena are gamma ray bursts, and a sufficiently close one could annihilate Earth's atmosphere. Such a planet-destroying burst would likely originate from the merger of 2 collapsing stars in a distant galaxy, creating an event of unbelievable power and brightness. If a gamma-ray burst occurred just 1,000 light-years away from us, it would appear as luminous as our own sun. Our planet's atmosphere would attempt to shield us, but this natural defense would quickly fail. The radiation would be so powerful, it would effectively burn away the atmosphere, triggering the creation of nitrogen oxides that would demolish the ozone layer. Without that vital protection,
the sun's ultraviolet rays would mercilessly strike Earth's surface. This intense radiation would first eradicate the small oceanic plankton that generate between 50 and 70% of the world's oxygen. Their demise would lead to a catastrophic oxygen shortage, precipitating the extinction of most life on the planet. Over time, the relentless heat and ultraviolet radiation from the sun would transform Earth into a vast, barren rock, entirely devoid of life. Now, what if we were to cross paths with a rogue black hole? You probably know that a black hole is a cosmic region where gravity is so immense that nothing, not even light, can break free. The closest known black hole is a comforting 1,500 light-years away, which might suggest we are safe. However, the existence of wandering, rogue black holes makes the situation far more precarious.
Should such a cosmic behemoth drift into our solar system, Earth would be utterly doomed, with no possibility of survival. In 2020, 13 rogue black holes were detected, but they are situated roughly 1 billion light-years from us, a considerable distance in cosmic terms. So, we have some time, and it's important to remember that the likelihood of such a catastrophic encounter remains exceedingly low.
Another potential doomsday scenario involves an alien planet dislodging Earth from the habitable zone, pushing it into an extreme orbit much farther from the sun. This would cause the climate to plunge into a deep freeze across the globe. As our planet moved farther from the sun, the star's gravitational influence would weaken, and Earth would eventually become a lifeless, frozen sphere encased in a thick shell of ice. Alternatively, the sun itself will eventually expand into a red giant, which will completely reshape the habitable zone of our solar system. This catastrophic event will start when the hydrogen in our star's core is depleted, setting off a chain reaction that makes the core hotter and denser. Consequently, the sun will swell to a monstrous size, and in the process of its transformation, it will consume Mercury, Venus, and our own planet. In the early morning hours of June 30th, 1908, a cataclysmic explosion ripped through the sky above the stony Tunguska River in Siberia. The blast obliterated 80 million trees and devastated an area of more than 820 square miles. Thousands of people located within a 900-mile radius saw the Tunguska event, and researchers later gathered over 700 eyewitness testimonies. Most of these accounts described a fireball streaking across the sky, shining with the intensity of a second sun. Witnesses also reported a series of terrifying explosions that produced horrifying sounds. Shortly after, the ground began to shake violently, and according to some, it split open, swallowing everything into an abyss. But is this an accurate depiction of what occurred? Scientists are not entirely sure. The local Yakut and Evenki peoples, for instance, held a belief that a deity had unleashed the fireball to cleanse the world of humanity forever. Meanwhile, numerous meteorological stations across Europe detected significant atmospheric and seismic waves. In the days that followed, bizarre phenomena were witnessed over vast territories reaching into Europe, including glowing clouds, vibrant sunsets, and even a faint illumination of the night sky. International newspapers at the time speculated about a powerful volcanic eruption, while some scientists proposed it could have been a cosmic impact. Unfortunately, the region where the event took place was extremely difficult to access, which significantly delayed any scientific inquiry into the matter. It wasn't until 1921 that a mineralogist named Leonid Kulik grew interested in the incident. His curiosity was sparked by a newspaper article that made the sensational claim that passengers on the Trans-Siberian Railway had witnessed the collision, and some had even touched the still-warm meteorite. Kulik organized an expedition and traveled to the area, where he began to examine reports of the event. Although he quickly discovered that the story about the train passengers was pure fiction, Kulik and his team were undeterred and continued their investigation.
The expedition made its way into the region, initially navigating the Angara River before continuing along the Tunguska River. On April 13, 1927, the researchers came upon a vast expanse of forest where the trees had been completely leveled by some tremendously powerful force. Curiously, the only trees that showed signs of being scorched were located directly at the explosion's epicenter. And even more perplexing, a thorough survey of the area revealed no impact crater or any meteorite fragments. In the autumn of that same year, Leonid Kulik's report on the incident was picked up by newspapers both at home and abroad. The scientist proposed that the immense explosion and resulting devastation were caused by an iron meteorite that had detonated in the atmosphere. He attributed the absence of a discernible impact site to the marshy landscape, suggesting the soft ground may have absorbed the impact without forming a conventional crater, and so, despite the lack of direct evidence, Kulik initially named the phenomenon the Filimonovo meteorite, after the railway station where witnesses saw the brilliant flash in the sky. Only later did the incident gain its more famous name, the Tunguska event, and despite its global renown, there is remarkably little scientific data that describes what happened. Since 1928, over 100 expeditions have ventured to the site to collect samples of soil, rocks, and wood. Yet the findings have consistently been inconclusive. Some records of seismic and atmospheric waves captured just after the blast have survived. And about 30 years after the event, a map of the flattened forest was finally created. The scarcity of reliable information about a crater or meteorite fall, combined with conflicting eyewitness accounts, has given rise to a multitude of theories over the decades. These explanations range in plausibility, from an asteroid merely grazing Earth's atmosphere to the passage of a primordial black hole straight through the planet. In the universe's current era, black holes are formed when giant stars exhaust their nuclear fuel and collapse under their own immense gravity, meaning there is a fundamental limit to how small a modern black hole can be. It must originate from a star roughly 20 times more massive than our Sun. However, primordial black holes represent an entirely different theoretical concept, as their existence has not yet been confirmed. These hypothetical objects could have originated in the first few moments after the universe began, a time when the matter that would eventually form stars and galaxies was incredibly compressed. In this early stage, pockets of hot material might have become dense enough to collapse into black holes of all sizes, from those weighing 100,000 times less than a paperclip to others with masses equivalent to 100,000 suns. Shortly after this period, the universe underwent rapid expansion and began to cool, which brought an end to the conditions necessary for primordial black holes to form. While we have yet to observe any of these ancient objects, their formation right at the dawn of the universe makes it plausible that they could still be traveling through space. In fact, some ideas suggest that primordial black holes, smaller than an atom, could be passing through our planet every day without causing any harm, while a larger one might pass by on a much rarer timescale, perhaps once every 1,000 years. After delving deeper into the Tunguska event, a team of physicists published a paper in the journal Nature in 1973, postulating that the event itself could have been the result of a primordial black hole traversing the planet. The scientists argued that a black hole with the mass of a large asteroid would neatly explain the absence of a crater or any other physical signs of an impact. The blue light reported by witnesses also aligns with this theory, as the radiation from the shock wave would be re-emitted at longer, visible wavelengths, making the plasma column appear a deep blue. Of course, this is a highly unconventional theory,
But the research team also offered a method to test their claim, searching for evidence of an exit point on the opposite side of the planet. They reasoned that a black hole moving at such high velocity would lose only a tiny fraction of its energy while passing through Earth, allowing it to travel in a nearly straight line. The resulting exit location, along with potential shock waves and oceanic disturbances in that region, could serve as a definitive test of the entire hypothesis.
However, there is a significant problem with this idea. A black hole passing through Earth could potentially become trapped by our planet's gravity. If captured, it would settle in the core and begin to consume our world from the inside out. Furthermore, as the black hole collected vast amounts of matter during its transit, the process would generate an incredible amount of heat, releasing energy almost equivalent to the asteroid impact that led to the extinction of the dinosaurs.
Fortunately, existing calculations indicate that the probability of a black hole being captured by our planet's core is exceedingly low, as these cosmic objects typically move far too quickly. The notion that the Tunguska event was caused by a black hole passing through our planet is undeniably compelling, yet no solid evidence has ever emerged to support it, and we still don't even know if primordial black holes truly exist. Our solar system is teeming with enigmatic objects appearing from all corners of space, such as the mysterious interstellar visitors spotted by researchers in Hawaii in October 2017, which they named Oumuamua.
In the Hawaiian language, its name translates to a scout from a faraway land. This object was on a trajectory that saw it escape the gravitational pull of its home world, much like a ball launched into the cosmos with no chance of coming back. This confirmed that the peculiar visitor originated outside our solar system, igniting a wave of speculation that ranged from a common asteroid to a craft from another civilization, with some scientists even postulating it was a fragment of nitrogen ice from a Pluto-like world. The mystery was deepened by its bizarre shape, as significant fluctuations in its brightness suggested a form that was either long and thin like a cigar, or extremely flat like a disc. Furthermore, Oumuamua defied easy classification, behaving neither like a typical comet nor an asteroid. While icy comets develop brilliant tails near the Sun, and asteroids are simply tailless rocks, this object had no tail and emitted no gas. Yet its highly reflective, almost metallic surface and its baffling acceleration as it passed the Sun, a push not caused by our star's gravity, set it apart from any ordinary space rock. Following extensive study, researchers have proposed a compelling theory. Oumuamua was likely a comet coated in frozen hydrogen. This surface layer would have reacted to sunlight, creating the thrust that accelerated the object and changed its path. Scientists believe this hydrogen accumulated over a vast period of exposure to cosmic radiation, a process that also imparted a distinctive reddish hue to its surface. The origin of Oumuamua is thought to be a young, tumultuous star system, where planetary migrations and frequent collisions are common. These environments are known to fling countless small bodies into interstellar space. It is plausible that a massive, Jupiter-like planet ejected it with its immense gravitational force, a familiar scenario for how many comets are cast out from their own systems. While Oumuamua has now departed our solar system, we believe similar interstellar visitors pass through about once a year. To better understand these enigmatic travelers, astronomers are devising a mission to pursue Oumuamua, planning to use the gravitational assists from Earth and Jupiter to propel a probe to the necessary velocity for an intercept. Not all unexpected guests make such a brief appearance. In October of 2019, the Hubble Space Telescope captured a blue-tinted comet trailing dust and gas, located between the orbits of Mars and Jupiter at approximately 260 million miles from our planet. Although the luminous cloud of dust around it was visible, its core remained hidden from view, being too small to resolve.
Of course, small is used in a cosmic sense. The nucleus is estimated to be about 3,200 feet across, comparable to the length of 9 football fields. By March of 2020, Hubble imagery revealed that a piece had fractured from its core, confirming that this comet was far more active than Oumuamua. Further analysis showed its nucleus to be a fragile combination of ice and dust, with a varied surface of rugged areas and smoother deposits of icy debris.
Its discovery is credited to amateur astronomer Gennady Borisov, leading to its official designation, Comet 2I/Borisov. Experts swiftly verified its interstellar origins, and it was certainly a swift traveler, clocking in at a staggering speed of roughly 110,000 miles per hour, a velocity sufficient to orbit the Earth 4 times in a single hour. This particular visit was captivating for a number of reasons. The majority of comets native to our solar system hail from either the Kuiper Belt, a vast, ring-like zone of icy bodies beyond Neptune, or the even more remote Oort cloud, a colossal sphere of ancient objects from which most long-period comets emerge. Researchers theorize that Comet Borisov almost certainly originated in a different star system, one that could be either more or less mature than our own. Whatever its home, it was probably expelled from its native system in a manner similar to Oumuamua. Despite being too small to hold a permanent atmosphere, Borisov formed a coma as it neared the Sun, the term for the lovely, glowing envelope of gas and dust that surrounds a comet's core. Unlike the fleeting Oumuamua, this visitor lingered, providing a much better opportunity for study and revealing it had never passed close to another star before its journey here. Regrettably, Borisov's visit also came to an end, and it is now on a course that will carry it back into the void between stars. Speaking of spectacular comets, you might recall the Great Comet of 1996, which was given the name Comet Hale-Bopp. It too was named for its discoverer, an astronomer named Eugene Hale-Bopp, and was found in a fortunate twist of fate on New Year's Eve, March 25, 1996. This comet made an exceptionally close pass by Earth, coming within just 0.1 astronomical units, and journeyed over the North Pole, marking one of the nearest cometary approaches of the past 200 years. The spectacle was visible across the globe as a stunningly bright object in the expanse of the night sky, and its performance lasted far longer than a single evening. Its visibility steadily increased throughout March, and by the month's conclusion, it had become one of the most brilliant fixtures in the heavens, not fully vanishing from sight until the end of May. Hale-Bopp is a long-period comet, requiring centuries to circle the Sun. Its previous visit was some 17,000 years ago, and its orbital period has now been extended to 70,000 years. But you shouldn't feel let down. Many other comets are destined to illuminate our skies in the future. However, certain celestial bodies have a tendency to linger in their orbits for much longer periods. Let's consider an asteroid with a name so complex that I wouldn't dare attempt to pronounce it. In Hawaiian, it translates to Jupiter's mischief maker. But fortunately, scientists simplified it for us, giving it the nickname BZ. This minor celestial body measures only about 1.8 miles in diameter, and as you might infer from its name, it shares an orbit with Jupiter. The twist, however, is that this asteroid travels in the opposite direction, a path known as a retrograde orbit. This peculiar asteroid was first identified in November of 2014. It completes one trip around the Sun in approximately 11 years and 8 months, periodically weaving both inside and outside of Jupiter's orbital path. This cosmic dance has been ongoing for at least 1 million years, and is expected to persist for another 1 million. The question of its strange motion leads to a fascinating theory. BZ could be an immigrant from interstellar space.
it might have drifted past our solar system about 4.5 billion years ago during its formation, becoming ensnared by gravity while still maintaining its contrary orbit. Alternatively, BZ could have originated from the Oort cloud, a distant repository of icy objects at the edge of our solar system. If that's the case, its bizarre trajectory may have been shaped by the gravitational pull of the enigmatic Planet 9, a hypothetical world thought to exist far beyond Jupiter. Regardless of its origin, this asteroid enhances our comprehension of the solar system's history and the potential ways organic materials from deep space could have reached us. Our solar system constantly hosts thousands of such objects from beyond, each staying for a different duration, but they occasionally offer us incredible insights into interstellar space.
Throughout history, different cultures have developed their own interpretations of these celestial visitors. For instance, the inhabitants of the Andaman Islands, a community in the Bay of Bengal, view them as fiery torches hurled through the sky by spirits of the forest. Similarly, some Australian Aboriginal groups perceive them as burning sticks that shamans ride across the heavens. If you were to consult an astronomer, however, you would receive a more scientific explanation. A comet is a vast object composed of dust and ice that follows a path around the sun. Perhaps the most renowned of these cosmic travelers is Halley's Comet, a celestial body that has left a profound mark on human history and our understanding of these mysterious phenomena. When it neared our planet in August of 1835, it was blamed for a fire in New York that raged for several nights. Around the same time, the Sioux tribe in Florida interpreted the comet's long tail as a sign that they would soon lose their independence. The comet's return in 1910 once again fueled fears, with many seeing it as a harbinger of doom. During that 1910 appearance, people in Chicago went to great lengths to seal their windows, hoping to shield themselves from the comet's supposedly toxic tail. Others rushed to purchase all sorts of strange contraptions, from protective umbrellas to special comet-proof masks. So what is it about this celestial object that captures our imagination? Why does it periodically grace our skies? And more importantly, does it actually pose a threat? Astronomers classify Halley's Comet as periodic because it returns to our vicinity roughly every 75 years, offering a rare few the chance to witness it twice in a lifetime. The comet's last flyby of Earth occurred in 1986, with its next scheduled appearance set for 2061. Despite this predictable timetable, its exact orbit is difficult to forecast with perfect accuracy. This uncertainty arises partly from the chemical reactions happening within the comet itself, as well as from random gravitational interactions with other planets and objects in our solar system. Its official designation, 1P/Halley, pays tribute to the English astronomer Edmund Halley, who was instrumental in understanding its nature. Edmund Halley meticulously studied historical accounts of a comet that approached Earth in 1531, 1607, and 1682. Through his calculations, he astutely concluded that these were not three separate comets, but rather repeated appearances of the very same object. He even predicted its subsequent return in 1758. Although Halley sadly passed away before he could see his prediction come true, the comet was rightfully named in his honor for his groundbreaking discovery. According to the European Space Agency, the earliest confirmed sighting of Halley's Comet traces back to March 30th, 239 BCE, an event documented by Asian astronomers in the Shiji and Wenxian Tongkao chronicles. Another study suggests we may have seen it even earlier, in the era of the ancient Greeks. Records from that time describe a massive meteorite that struck northern Greece, baffling the locals,
and quickly becoming one of the ancient world's most famous tourist sites. The authors of these accounts also noted a comet in the sky at the time of the impact, reporting that the object was visible for about 75 days.
Even William Shakespeare seems to have been inspired by this comet, writing about it in his play Julius Caesar around the year 1600. It was in this work that he penned the now famous line, "The heavens themselves blaze forth the death of princes," associating comets with monumental events. This was not the final instance of a writer feeling a personal link to this object. In 1909, the author Mark Twain famously declared, "I came in with Halley's Comet in 1835. It is coming again next year, and I expect to go out with it." True to his word, Twain passed away on April 21, 1910, just one day after the comet had made its closest pass to the Sun.
We gained a much clearer view of the comet during its most recent visit in 1986, thanks to significant advancements in technology. A flotilla of spacecraft, aptly named the Halley Armada, was dispatched to intercept the comet and analyze its composition. One of these probes successfully captured the first-ever close-up images of a cometary nucleus. At the same time, vastly improved telescopes on Earth allowed us to observe its journey past our planet with unprecedented detail.
Based on all current research, the probability of Halley's Comet presenting any real danger to Earth is incredibly slim, and most of the calamitous events attributed to it were pure fiction. In fact, comets may have been crucial for the emergence of life on our world. Many experts propose that during our planet's early history, impacts from comets delivered substantial quantities of water, which were essential for forming our oceans. Furthermore, these cosmic wanderers may have also seeded Earth with the fundamental organic materials necessary for life to begin. It's crucial for you to understand that comets are not the same as asteroids. Whereas asteroids are compact, stony celestial objects that also circle the Sun, comets are primarily made of frozen compounds like ammonia, methane, or water, including only a minor amount of rock. This specific composition has led to comets often being referred to as dirty snowballs, and they are structured in 4 parts: the nucleus, the coma, the dust tail, and the ion tail, with the nucleus accounting for the bulk of the comet's entire mass. While we have identified over 3,000 comets, astronomers speculate that as many as 1 billion may exist within our solar system. When a comet becomes brilliant enough to be seen from Earth without any optical aid, it earns the title of a great comet, an event that occurs roughly once a decade. Although people have witnessed comets for thousands of years, scientists now understand that their lifespans are quite short, perhaps only a few thousand years, because they lose a tremendous amount of material with each pass near the Sun. This brief existence, when compared to the solar system's age of 4.6 billion years, presents a puzzle. The fact that these cosmic bodies are still observable today implies there must be a replenishing source for them somewhere in the cosmos. Otherwise, they all would have vanished long ago. Take, for example, the comet Hale-Bopp, which made a close approach to Earth in January 1997. The last time it was visible from our planet was back in the Bronze Age, approximately 2000 BCE. This particular comet, known for being significantly larger and more impressive than Halley's Comet, has a nucleus that measures 24 miles across and can potentially be viewed from Earth's surface with the naked eye. Meanwhile, Comet Borrelly holds the distinction of being the second comet ever to be examined at close range by a spacecraft. The theory that the Tunguska event was caused by a black hole traversing our planet remains a fascinating idea, but it lacks any solid supporting evidence, and we still aren't even certain that primordial black holes actually exist. For millennia, humanity has looked up into the glittering expanse of the night sky. initially with a sense of superstitious fear and wonder. The ancient peoples projected images of gods, heroes, and mythical beasts onto the star patterns, creating constellations and telling epic stories. Yet, buried beneath those layers of myth, a different kind of curiosity was always present. The idea that other worlds, maybe even ones like our own, could exist in that vast, unreachable distance. This notion, at first a quiet philosophical musing, grew into a major driving force for scientific exploration. For centuries, the stars were seen as nothing more than tiny sparks of light, their true nature a complete mystery. We were familiar with our home, Earth, and could see the other planets in our solar system as wandering lights that behaved differently from the fixed stars. To imagine planets circling other suns was a concept left to visionaries and writers of fiction. As science progressed, however, the development of ever more powerful telescopes and observational tools began to dissolve the barrier between imagination and fact. We came to understand that stars are actually distant suns, enormous, intensely hot globes of gas, much like our own. This realization prompted an obvious question. If our sun hosts a family of planets, why shouldn't other stars have planetary systems as well? This inquiry marked the beginning of the modern search for exoplanets. So, what exactly is an exoplanet? The prefix exo is derived from the Greek word for outside, which means an exoplanet is any planet found outside of our solar system, in orbit around another star. Think about our own cosmic neighborhood, the Sun and its 8 orbiting planets. Now, try to imagine that there are countless such systems throughout the universe, possibly billions or even trillions of them. Every single point of light you see in the night sky is a potential sun, nurturing its own unseen worlds. Discovering these distant worlds has evolved into one of the most thrilling and formidable challenges in contemporary astronomy. But you might ask why we even search for them. What compels scientists to dedicate their lives to building sophisticated instruments and sifting through immense data sets, all to find tiny objects trillions of kilometers away? The motivation is rooted in the core of human nature, our unquenchable thirst to comprehend the universe and our own place within it. The ultimate question fueling this quest is as ancient as humanity itself. Are we alone? Does life, whether intelligent or simple, exist anywhere else? And at the heart of it all is the most exhilarating possibility. Is there, somewhere out there among those innumerable stars, another planet just like Earth? A world with oceans, continents, and a breathable atmosphere, a place that could be a second home for life, or perhaps for humanity itself in the far future. This pursuit transcends simple scientific curiosity. It touches upon a profound existential need to know if we are a unique accident or if life is a common occurrence on a cosmic scale. Finding a second Earth would completely transform our understanding of the universe and of ourselves. It would trigger a revolution in human consciousness, on par with the discovery that the Earth orbits the Sun, which is why every new exoplanet candidate, particularly one in its star's habitable zone, generates so much excitement. You and I stand at the cusp of monumental discoveries, gazing into the cosmic depths in hopes of finding evidence of other worlds. This is a truly grand adventure, a cosmic odyssey that involves all of humanity, even if our participation for now is limited to telescopes and intricate calculations. We first started posing questions to the stars thousands of years ago. Today, equipped with advanced knowledge and technology, we are finally starting to get the first, incomplete, answers on the most exciting journey of all, the search for other Earths across the infinite ocean of stars. Just try to grasp the challenge of this task. Finding a minute,
non-luminous sphere, perhaps the size of our Earth or even larger, that is orbiting a star so far away that its light requires tens, hundreds, or even thousands of years to travel to us. Trying to see an exoplanet directly is like attempting to spot a single firefly sitting on a massive searchlight from many miles away. The challenge is immense because the parent star's brilliance outshines the planet's faint, reflected light by a factor of millions, sometimes even billions. So how can astronomers possibly locate these hidden worlds? They operate like cosmic investigators, not looking for the planet itself, but for the subtle evidence it leaves behind in its star's light or movement. This is the delicate art of detecting indirect clues, a process that demands extraordinarily precise instruments and a great deal of patience. One of the most fruitful techniques in this cosmic hunt is the transit method. The principle behind it is both simple and profoundly elegant. If you are fortunate enough to be observing a system where the planet's orbit is aligned just right, it will periodically cross in front of its star from your perspective. For that brief period, the planet eclipses a minuscule fraction of the star's disk, causing a very slight, yet regular and predictable dip in the star's observed brightness. Picture yourself gazing at a streetlight far in the distance, and every now and then, a tiny gnat flies across the bulb. You would register a faint, almost imperceptible flicker. In this cosmic scenario, the gnat is an entire planet, dwarfed by the stellar lamp, and the distances involved are astronomical. The reduction in the star's light during a transit is typically just a fraction of a percent, sometimes as little as 1/100%. Detecting such minute fluctuations requires incredibly sensitive telescopes, which are often positioned in space to escape the blurring effects of Earth's atmosphere. Renowned space-based observatories like the Kepler and TESS telescopes were designed specifically for this purpose. They have relentlessly monitored hundreds of thousands of stars, looking for these signature dimming events. Beyond merely detecting a planet's presence, the transit method also allows you to estimate its size, as a larger planet will block more light. Furthermore, by timing the interval between these transits, you can determine the planet's orbital period, which in turn helps you calculate its distance from the star. Another formidable instrument in the exoplanet hunter's toolkit is the radial velocity method, which you might also hear called the Doppler method or the wobble method. This technique is rooted in the law of gravity. While we tend to think of planets orbiting stars, the reality is that both bodies orbit a shared center of mass. Because the star is so much more massive, this point is located very near the star's core, but is not perfectly aligned with it. This means that as the planet circles its star, the star itself is pulled into a small, corresponding orbital dance. To visualize this, imagine a large adult holding hands with a small child and spinning around. The adult wouldn't stay perfectly still, but would also move in a small circle to counterbalance the child. You cannot see a star's physical wobble directly across such vast distances, but you can measure its impact on the light it emits. When the star moves slightly toward you in its dance, its light waves are compressed, shortening their wavelength and shifting them toward the blue part of the spectrum. Conversely, as it moves away, the light waves are stretched, increasing their wavelength and causing a shift toward the red end of the spectrum. This phenomenon is the well-known Doppler effect, the same principle that causes the pitch of an ambulance siren to change as it speeds past you. By meticulously measuring these tiny periodic shifts in a star's spectral lines, astronomers can confirm the existence of an unseen planetary companion. They can also estimate its minimum mass, since a more massive planet orbiting more closely will induce a stronger gravitational tug, causing a more pronounced wobble in the star. These two primary approaches, the transit and radial velocity methods, function like two complementary detective tools. One reveals the planet's size, while the other gives you its mass. With both size and mass, you can then calculate the planet's average density, offering the first critical insights into its composition. This helps you begin to understand whether you are looking at a dense, rocky world like Earth or a low-density gas giant like Jupiter. Naturally, other, more exotic detection techniques exist. There's gravitational microlensing, where a star and its planet's gravity can act like a lens to briefly magnify the light of a far more distant star. Direct imaging is also possible, though exceedingly rare and typically limited to very large planets situated far from their star's blinding glare. However, it is the transit and radial velocity methods that have provided the overwhelming majority of our knowledge about extrasolar worlds, empowering astronomers to solve the mysteries of distant star systems from the faintest of clues. When scientists first began their dedicated search for planets beyond our solar system, many assumed they would discover systems arranged much like our own, smaller terrestrial planets in close orbits, with large gas giants farther out. The truth, however, proved to be far stranger and more varied than even the most creative theories had predicted. The universe, it seems, possesses a boundless imagination for world building, and the planetary menagerie we've uncovered is nothing short of breathtaking. A prime example of these early, startling discoveries were the so-called hot Jupiters, often identified through the radial velocity method. Picture a planet as large as Jupiter, or even larger, that orbits its star not in the cold, distant reaches of its system, but so close that it completes a full revolution in a matter of a few Earth days, or in some cases, even hours. These worlds are roasted to temperatures high enough to melt metals, their atmospheres puffed up and continuously being stripped away into space by ferocious stellar winds. On some of these worlds, a full year passes more quickly than a single week on Earth, and their very discovery sent shockwaves through the scientific community. According to traditional planet formation theories, gas giants were expected to form in the cold, distant reaches of a solar system, where ice could condense and act as a seed for these colossal bodies. The finding of these so-called hot Jupiters forced a complete overhaul of existing models, introducing the idea that giant planets can migrate from their distant birthplaces, moving closer to their star and clearing any objects in their path. This revelation demonstrated that the histories of planetary systems can be far more violent and dynamic than we ever imagined from the vantage point of our own relatively orderly cosmic neighborhood. But the surprises didn't stop there. As our methods for detecting planets improved, particularly with instruments like the Kepler Space Telescope, a remarkable fact came to light. A class of planet that is incredibly common throughout the galaxy is entirely absent from our own solar system. These worlds are known as super-Earths. They are planets with a mass and diameter greater than Earth's, but substantially less than that of ice giants, such as Uranus and Neptune, placing them in a fascinating intermediate category. Some of these super-Earths are likely just scaled-up versions of rocky planets like Earth or Mars, potentially featuring stronger gravity and a much thicker atmosphere. Others could be water worlds, entirely enveloped by a deep, global ocean. At the upper end of the scale, bordering the ice giants, they might be akin to mini-Neptunes, worlds with a solid core surrounded by an exceptionally vast and dense envelope of hydrogen and helium, yet not massive enough to qualify as full-fledged gas giants. The sheer existence of this diversity within a single mass range presents new challenges for scientists. Why does our solar system have such a pronounced gap between the size of Earth and Neptune? What specific conditions give rise to the formation of a super-Earth versus a mini-Neptune? And could any of these worlds, however different from our own, be potentially habitable? This class of exoplanets remains one of the most compelling subjects for future astronomical investigation. However, the cosmic menagerie contains even more peculiar inhabitants. Astronomers have uncovered evidence of lava worlds, planets orbiting so close to their stars that their entire surface is a churning ocean of molten rock. There are also strong candidates for ocean worlds, where hundreds of kilometers of water might lie hidden beneath a dense atmosphere. We have found planets orbiting binary stars, where two suns grace the sky, in a scene reminiscent of Tatooine from Star Wars. There are even planets orbiting pulsars, the dead, rapidly spinning remnants of supernovae, where conditions can only be described as infernal.
There are even hypotheses about the existence of rogue planets, celestial bodies that have been ejected from their home systems and now drift alone through the blackness of interstellar space. Each discovery of this nature broadens our definition of what a planet can be. It has become clear that the universe isn't simply a factory for churning out copies of our solar system. It is an incredibly imaginative architect, capable of creating worlds of every conceivable size, composition, and orbital configuration. This incredible planetary zoo has forced us to recognize that our own solar system is just one of countless possible arrangements, and quite possibly not even a typical one. By studying this incredible diversity, we gain a deeper understanding of the fundamental processes that govern the formation and evolution of all planets, including our own, which in turn makes the quest for a second Earth all the more thrilling. After all, we now have a much clearer picture of just how broad the spectrum of possible worlds truly is. Amid this staggering variety of worlds that we've discovered across the galaxy, the search for a planet that mirrors our own, a true second Earth, holds a unique place in the minds of both scientists and dreamers. But what qualities are we actually searching for? What specific criteria could make a distant world potentially capable of supporting life as we understand it? There is essentially a recipe for habitability, a collection of key ingredients we believe are essential for life to emerge and sustain itself. The most crucial of these is thought to be liquid water. Here on Earth, every known life form, from the smallest bacterium to the largest whale, is dependent on water in some way. It functions as a universal solvent, a medium for biochemical reactions, and a transport system within living cells. Consequently, the search for potentially habitable worlds is primarily a search for planets where water can exist as a liquid on the surface. This requirement is directly tied to temperature, which is determined by a planet's distance from its parent star. This brings us to the concept of the Goldilocks zone, or what is more formally known as the habitable zone. This is the orbital region around a star where it is neither too hot for all water to boil away into space, nor too cold for it to be locked away as permanent ice. A planet must reside at just the right distance, much like in the fairy tale where the porridge was just right. A world too close to its star, like Venus, risks becoming a runaway greenhouse furnace, while one too far, like Mars, can become a frozen desert. Of course, the habitable zone's location and width are entirely dependent on the star itself. For brilliant hot stars, this zone is situated farther out and is more expansive. For dim, cool red dwarfs, it is much narrower and huddles very close to the star. However, orbiting at the correct distance is not the only requirement. The planet's size and mass are also critically important. A world that is too small, like Mercury or Mars, will lack the gravitational pull needed to hold on to a thick atmosphere, which is essential for stabilizing climate and shielding the surface from dangerous cosmic radiation. On the other hand, if a planet is too massive, it will likely gather a colossal amount of gas during its formation, becoming an ice or gas giant like Neptune or Jupiter, where it is difficult to imagine Earth-like life ever taking hold. The perfect candidate planet would have a mass and size similar to our own,
making it substantial enough to hold on to an atmosphere and potentially sustain geological processes. Things like volcanism and plate tectonics are vital for recycling substances on Earth, so their presence would be a significant indicator. Of course, a crucial factor is the existence of an atmosphere with the right density and composition, as this is fundamental for habitability.
This atmospheric layer serves as a thermal blanket, moderating the extreme temperature swings between day and night, and it provides the necessary surface pressure for liquid water to remain stable. Furthermore, it could hold gases like oxygen or methane, which can serve as potential, though not conclusive, signs of biological processes. A planet's atmosphere and its magnetic field, both often tied to its size and internal dynamics, also act as a critical shield, deflecting harmful stellar radiation and cosmic particles.
Given these factors, the search for a second Earth leads astronomers to focus on rocky, Earth-sized planets that orbit within their star's habitable zone. The primary hunting ground for this search is around stars resembling our own Sun, which are known as G-type stars. This focus makes sense, as we have definitive proof that such a star can support a life-bearing world, our own. The issue, however, is that stars like our Sun are not especially common.
Red dwarfs, which are small, dim, and have incredibly long lifespans, are far more abundant throughout the cosmos.
Planets are frequently discovered orbiting these stars, often within their compact, habitable zones that lie very near the star itself. This proximity actually makes these worlds simpler to find using observational techniques like the transit method and radial velocity measurements, which look for dips in starlight or stellar wobbles.
The entire field of exoplanet hunting has evolved dramatically.
From its early days of trying to detect the slightest stellar movements or minuscule drops in a star's brightness, we have since mastered the art of finding these worlds beyond our solar system, uncovering their incredible diversity and pinpointing the key characteristics of potentially habitable planets. Now we are embarking on a far more ambitious journey.
We are now aiming to transition from merely detecting and cataloging these distant worlds to studying them in great detail. The goal is to probe their atmospheres, and in doing so, perhaps uncover the answers to some of humanity's most profound questions. Leading this new wave of exploration are some of the most powerful and sophisticated instruments ever built, true marvels of modern engineering. In this endeavor, modern astrophysics is placing its greatest hopes on the James Webb Space Telescope, or JWST. This massive infrared observatory, positioned far from the distorting effects of our planet's atmosphere, offers unparalleled sensitivity and clarity. Its main purpose isn't necessarily discovering new planets, although it is capable of that, but rather conducting in-depth studies of known candidates, especially those orbiting nearby red dwarfs.
So, how can the James Webb Space Telescope and its successors actually analyze the atmosphere of a planet that is trillions of kilometers away? The answer lies in elevating the transit method to a whole new level of precision. As a planet crosses in front of its star from our perspective, a fraction of the starlight filters through the thin veil of its atmosphere before it reaches the telescope. The various gases in that atmosphere absorb light at very specific wavelengths, imprinting a unique chemical fingerprint onto the star's spectrum.
By carefully analyzing these minute alterations in the starlight during a transit, scientists can decipher which gases are present in the exoplanet's atmosphere, much like you might determine the contents of smoke by observing how it filters light. The ultimate objective of this sophisticated analysis is the hunt for biosignatures, which are telltale indicators of life. Scientists are searching for particular molecules that we associate with biological processes here on Earth. First on the list is water vapor, as its detection would confirm the existence of the most essential ingredient for life as we know it.
Next is oxygen, a gas that, on our planet, is overwhelmingly produced by photosynthetic life. Discovering oxygen on another world would be a momentous event, although it wouldn't be absolute proof of life, since geological activity can sometimes produce it as well. Methane is another molecule of great interest. While it is produced by countless organisms on Earth, it can also arise from non-biological sources. For this reason, identifying specific combinations of gases that are hard to explain through geology or chemistry alone would be especially compelling. For instance, finding significant quantities of both oxygen and methane at the same time would be a powerful indicator, as these gases naturally destroy each other and would require a constant source, like active biology, to be replenished.
However, this entire endeavor is fraught with immense challenges. Exoplanetary atmospheres are incredibly tenuous layers, and the signals we need to capture are exceptionally faint. It demands the utmost precision in measurement and highly complex data analysis to isolate the true signal from background noise and instrumental interference. Moreover, we must become adept at distinguishing genuine biosignatures from phenomena caused by geological or photochemical processes to prevent any false alarms. Looking beyond transit spectroscopy, the dream is to one day directly observe these Earth-like worlds, to capture an actual image of them, even if it's just a tiny speck of light distinct from its star. Such an achievement would enable not only the direct analysis of their atmospheres, but also the monitoring of brightness changes, which could reveal a planet's rotation, the presence of weather patterns, or even the glint of oceans and continents. This, however, is an even more formidable task that will require the next generation of telescopes. We may need giant observatories on the ground equipped with adaptive optics that can cancel out the blur from Earth's own atmosphere, or perhaps even vast arrays of space telescopes flying in formation to act as a single, enormous interferometer. Yet, despite every difficulty, our relentless curiosity drives the search forward. What would it truly mean for us to find a habitable world? Even if the life it hosted were purely microbial, the discovery would be so fundamental that it would permanently alter our view of the cosmos and our own significance within it. It would suggest that life is not some unique miracle confined to Earth, but is instead a potentially widespread and natural outcome of the universe itself. A finding like this would surely inspire further research, perhaps one day resulting in the detection of complex or even intelligent life. The age-old question of whether we are alone serves as the primary impetus for this cosmic journey. We are only now beginning to pull back the curtain on the mysteries of worlds outside our solar system, with every new telescope, enhanced methodology, and recent discovery drawing us nearer to the truth. The search for a second Earth is far more than a simple scientific undertaking. It is an expression of our intrinsic need to investigate the unfamiliar, to reach out to the stars, and to determine our uniqueness in this vast and astonishing cosmos. The exploration goes on, and it is very likely that the most incredible discoveries are still yet to come.